The next is that is the alpha decay. That is alpha decay. The spontaneous process of emission of an alpha particles from a radioactive nucleus is called alpha decay. For example, suppose we have that element, it is disintegrated A minus of 4, Z minus of 2 plus 1 helium element plus this is the Q. So this is the parent nucleus, this is the daughter nucleus, this is alpha particle, and this Q is known as the centigrade energy. And the value of this Q, this is a kind of energy that is the mass of X minus mass of S initially, and this is actually we are going to find out the mass defect, that is m of X minus m of Y minus m of alpha. This is the m of alpha. So this is the mass defects that is to be multiplied with the c square. So we have a equation E is equals to mc square. From that side we are finding out this value. Some examples of alpha decay. The very first example is uranium 92 238. This is uranium is to be split in thorium 234, and this becomes 90 plus 1 2Hg. The second example is uranium 242, and that is the number is 24294. That becomes split in uranium 238, and this becomes of 92 plus He. The third is radium, that is Ra88, and this is 226. It is He42, and this radium, that is Rn, it becomes /2, and it is 222. So this is some example of alpha decay. Now the second is that is the beta decay, or we can write beta decay. The definition is the spontaneous process of emission of beta particle from a radioactive nucleus is called the beta decay. It is of basically of this is three types. The very first is the beta minus, which is represented as beta minus is here. So what is that? The beta minus means in this process of conversion of 0 and 1 into proton is 1H1 take place according to the following equation. And what is that equation? That is 0 and 1. It is to be replaced 1H1 plus minus this is, that is the beta minus, plus a anti neutron. This is the beta minus. And the example of this one is phosphorus, that is 1532. That becomes the sulfur, that is 16. The sulfur is 32 plus a anti-neutrino. So this is the beta minus decay. The another example of that is the beta minus. Now the beta plus, that is beta plus. In this type of decay, a proton is converted into a neutron and a positron. What is the positron? This is plus 1 E0. This is the notation of the positron, is emitted if nucleus has more proton than neutrons. What does it mean? It means it is 1H1, so it becomes 0N1 plus E0 plus 1. This is beta plus a anti-neutrino. For example, this is the process, and the example in this category, that is neon, that is the atomic number of this 1122. It will be split any 10, that is 22 plus E plus 1 0. This is the beta plus a anti-neutrino. And the third one, this is beta plus. The third one is, that is the beta minus beta plus, that is the electron capture. In this nucleus absorb one of the inner electrons which is revolving around it, and hence a nuclear protons becomes a neutron and a neutrino, that is these are emitted. And the process for this, that is 1H1 plus, it becomes 0N1 plus the neutrino. This is the process for the electron captured. Captured means to adhere, to accept that, to retain that. Now this is about the beta decay. Now we will talk about the third one, that is the gamma decay. That is gamma decay. It is the spontaneous process of emission of high energy photon from the radioactive nucleus, which means that is the energy of the gamma rays, that is h nu, that will be E1 minus of E0. E1 is means the higher energy level and this is the lower energy level. So this is the difference that will be equals to the amount of photons. So gamma rays are emitted by the not daughter nucleus. So it is understood that the emission of the gamma rays follows the emission of alpha and beta particles. So it is very clear because they are in the excited state. First of all, they will move in a ground state. After that, they are going to decay. For example, we are taking example of lead, that is the Pb. The atomic number is 82, the mass is 210. So it is the as we know, that is the half life of this is near about 22 years. It means that it emits a beta particle and a neutrino, and the daughter nucleus is formed. When it emits the beta particle, the daughter nucleus is formed. And when the daughter nucleus is formed, it is already in the excited state. When it is the excited state, it comes to the ground state, and when it will move from the excited to the ground state, the energy is in the form of the photon, and this is the gamma rays. So if diagrammatically I am going to discuss that is the lead, that is 80 to 210 lead. This is the energy level of E2. Now when it emits a beta particle, it becomes at the lower energy level, that is the E1, and this is the bismuth, that is 82 beta particles, so plus 183, and it is 210, but the star means it is in the excited state. Further, it will come down to the ground state, that is E is equals to 0. So when it will move from here to here, energy is released, that is h nu, and that is the gamma rays. And here when it becomes the stabilized, it becomes the bismuth 83 210. Here it is not excited. Here the excited is emits the gamma rays and becomes the stable. So if we'll write an reactions for this, that is lead to 1082, it will be go bismuth to 1083 at this level. This is the excited state, plus 0 minus 1, that is the beta particle, plus it is the anti-neutrino. Now this is further going down with the gamma rays, and it becomes the stable with the gamma rays. Now it is stable. This is not excited. This is the excited state. This is excited state. This is the ground state. It means it is stabilized. Now, the next is the nuclear reactions. The process, the process by which a stable nucleus is changed to another nucleus when it is bombarded by an energetic particles is called the nuclear reaction. This is the meaning of the nuclear reactions. Next is the nuclear energy. The energy obtained from the conversion of nuclear mass is known as nuclear energy. This is of two kinds. The first is the nuclear fission, and that another is the nuclear fusion. First, we will discuss about the nuclear fission. Nuclear fission is a process of splitting a heavy nucleus into two lighter nuclei along with the conversion of the mass defect into energy. For example, when a uranium 92-235 is hit by a neutron, then it will give you, it is unstable. 92 uranium unstable, and it will further disintegrate in the beryllium and the krypton. The beryllium is the 56 and the atomic weight is 141. Krypton is 36. The weight is 92. Along with this, we have a 3 neutron plus we'll get the energy, and this is the energy is near about 200 mega electron volts. So that so much energy is released when this uranium is to be hit by 1. The next which we are going to discuss. So this kind of reaction will be move in 1:3. So it is a kind of a chain reaction. When the one neutron is hit on the uranium, it will give you the 3 neutron. Again, this 3 neutron is to be hit by uranium. So every time it is going to the 3 times individual atom. So it gives you the lots of energy when the one neutrons with the uranium will give you. So the multiple, it will give you the massive. Now the next is energy released per fission of uranium 92 to 35. As we have written the earlier equation, I am writing once again, that is 92 to 35, 0 and 1, it give you unstable. 92 to 36, it give you beryllium 56, 141 plus krypton 36, 92 plus 3 neutrons again plus the amount of energy, that is Q. So we have to find out the energy released. For that we are going to find out the mass defect, and when we will get that mass defect, then we can easily find out the energy released per fusion. So first of all we are going to find out the mass defects. So for this one, it is the pre, it is the post. For this we are going to find out the mass defect. So the mass of uranium 92 235 is 235.124 AMU. Then the mass of neutron, this is equals to 1.009 AMU. Now the post section. This is, you can say that it is the pre-section or the mass of the product. Now the mass of the reactants we are going to find out. What is that? This is the uranium, this is the reactant, and this is the product. This is the product and this is the reactant. So reactant total mass is equals to 235.124 plus 1.009. It give you 236.133 AMU. This is 9. 5 to 36. Now the product side, right hand side. Next is, that is the mass of beryllium 56 141, that is equals to near about 140.958 AMU. The next is the mass of krypton, that is 3692. It is 91.926 AMU. This is the given values in the questions. Then the mass of 3 neutrons, that is 3.027 AMU. So the total mass of the product, that is equals to 140.958 plus 91.926 plus 3 neutrons, 0 to 7, that is AMU. It will give you 235.911 AMU. So the mass defect, that is the mass of a reactant minus the mass of the product, that is the 236.133 minus 235.911 AMU, and that will be 0.222 AMU, because we know that that is the A1 AMU is equals to 931 mega electron volt. So this, the energy Q, that is equals to 0.222 into 931 mega electron volt. It is give you 206.682 mega electron volt, which we are saying that is approximately 200 mega electron volt. So this kind of the calculation we are going to do. Now the one topic which is, that is the nuclear reactor. In nuclear reactor, the chain reaction is takes places. What does it mean? If with chain reactions mean chain reactions, what does it mean? Suppose this is uranium, we hit one neutron. So what is going then? With this it becomes the krypton. It give you the beryllium. This is further processing, and this give you one new uranium. The second uranium is here. The third uranium is here. With this we get the three neutron. This is neutron, this is neutron, and it will give the 3. So again this give you this kind of reaction. So every time it is multiplied by 3 times, so it becomes the chain reactions. So it is you can say it is a chain reactions of 2 types of chain reactions. The worst is, that is the uncontrolled chain reactions. What does it mean? You can write that if more than one neutron produced in a fission causes further fissions at each stage, then the number of fission and energy released will be multiply rapidly, and such a chain reaction is called uncontrolled chain reaction. For the best example of this one, that is the atom bomb. The next is, that is the second one, that is the controlled chain reactions. If only one neutron is available to cause further fission at each stage, then the amount of energy is released, and such a reaction is called the controlled chain reaction. The best example is the reactors where we are getting the electricity. That is the controlled chain reactions. Now, in the continuation of that, we are going to discuss that is the nuclear reactors. So, this is a device in which nuclear fission is maintained as a self-supporting yet called it is a controlled chain reaction. So I just draw a rough ray diagram for the nuclear reactor. This is a concrete chamber. This is to electric generator. This is the condenser. This is a heat exchanger. This is the another chamber. Again, this is the inside chamber where this is the cadmium rods. This is the filling of coolant to cool down the furnace. This is the coolant. This is the concrete wall. It is near about 7 or 8 meters concrete wall. The thickness of that wall is 7 to 8. So it is because of that in a fission reaction we are getting 200 mega electron volt energy. So that kind of energy if we have, then try to understand the 1000 temperature is there. To retain that, this is the thickness of the wall which is to be maintained. So these are the cores, these are the coolants. From here the coolant out, this is the coolant in, this is the pump which is helping to move down. This is the heat exchanger, means that this is the heat exchanger. So it is the condenser and this is the water is to be passed here in this heat exchanger. So the temperature is going to be reduced. So for that purpose we are going to use this water, and this is your turbine. So this is the sketch of the nuclear reactor. This is the sketch of the nuclear reactor. Now we are going to discuss the main parts of that one by one. So the main parts of the nuclear reactor. Mostly we have the 5 parts. Mostly. What are those parts? The first part, that is the fissionable material. One thing is left, that is here it is a moderator. It is the moderator. So first of all, the fissionable material, or you can say the fuel. The material used in this reactor is called the fuel. And mostly we are using the uranium material. The weight of this is 235. We can also use the thorium, 232. You can also use the plutonium. The symbol of that is Pu and the weight is 241. So they all are the isotopes and they all are mostly used as a fuel in the reactors. The second is, that is the moderator. What are the moderators? This is the moderators. So moderator is used to slow down the fast moving neutron, that is used to slow down the speed of the neutrons. So the most commonly used moderator is, that is the graphite, or we can say that is the water or the heavy water. The purpose is to reduce the speed of neutrons. This is the use of the moderator. So the third we will talk, that is the control material. What are the control material? Because as it is a chain reaction, so controlling is very important to maintain the constant rate of reactions. And the control material, for example, we are using here, it is the cadmium rod. These are the controlled material. So when we are interested to reduce down the rate of reactions, then what we are doing, we have a system, so that when we'll put that system on, then this cadmium rod is moved downward. So the reaction which is taken place here, it will slow down. So that is the control material, that is cadmium rods, which is to reduce the speed of reactions in the center of the furnace. The fourth is, that is the coolant. It's a very important thing, that is it is used to cool the material, and the using of this, the purpose is, this is the coolant, the excess heat which is generated due to the fission in this chamber, they can be moved out. So the commonly coolant which we are using in this kind of reactors, that is, you can use the water, that you can use the carbon dioxide, you can use the nitrogen, etc., so that the excess heat can be removed from that. So this is the excess, the coolant is to be heat up, and this will move here, the heat exchanger is here, water is here, so it will, when will move, the water is cold, the heat is hot, so this again, when it will move from here to here, the temperature is here higher, it is lower because the water is here, so again it will going in the same one. The fifth is, that is the protecting shield. What is the protecting shield? This is the protecting shield. This is the concrete wall, which we are saying, that is the concrete wall. It is 6 to 9 meters of thickness. Why it is important? Because it is a fission reaction, and the amount of that heat which is to be generated, that is near about in 1000 mega electron volt. So to reduce that, because it is a radioactive elements, if it is go in the environment, it will loss to everyone's life. So to control that, this amount of this the thickness of this wall is so that can be retain that heat inside, and it will not be break down. So this is the main thing. Now the working. What is the working here? So when the one uranium is to be hit by the one neutron, it will give you the beryllium and krypton plus 3 neutron plus 200 mega electron volt heat. So this is because of ones, and here there are so many uranium. The reaction is started. Suppose that we are having a so much neutrons, so there is a continuous chain reaction, and the amount which is the amount of heat which is generated in this chamber, that is extreme. So what we are doing, we are just slow down the reactions with the help of this cadmium rods. When the temperature or the reaction rate of reaction is very more, that's this cadmium rod will go down, and then the reaction will reduced or the stop, whatever the kind of working you want, you can control with this one. This from here, the heat which we are getting, that will go to the turbine. From turbine, it is good for the generation of electricity, and then the remaining heat which is condensed, it becomes water, and then again it will go in this chambers to cool down the heat which is coming from here. So this is the continuous process of the nuclear reactor. Now the next is the nuclear fusion. Fission is discussed. This is also known as thermonuclear reactions. So what is that? The definition of that can write a process in which two very light nuclei, means the atomic size is less than or equals to 8 when they are combined to form a nucleus with a large mass number along with the simultaneous release of the large amount of heat is called the nuclear fusion reaction. The fission one, that element is to be split two or more. Here the two small nuclei, they are come together and give the bigger nucleus. That is the disintegration. There is the assembling of that. For example, when the two, this is the deuterium atom is being added, then it will give you the helium plus one neutron plus the energy. This is the first example. The second example, when the hydrogen atoms, the four hydrogen atoms will come together, it give you the helium atom plus 2 neutrino plus the amount of heat. So in this case, the amount of heat that will be calculated, that is the mass. We have to find out the mass defect in this case. So that is the mass of 4 hydrogen atom minus the mass of 1 helium atom, and that is to be multiplied by c square. That E is equals to mc square is the formula which we are using. So this is 4 and the amount of weight is minus. This is the only one, that is 4002603 is the weight of that helium, and then AMU. So it will give you 0.028697 into 931 mega electron volt. So it is 26.7 mega electron volt. So this reaction will give you 1 helium plus 2 beta plus 2 neutrino plus the amount of heat, that is 26. So this is the example of thermonuclear reaction. The next which we are going to discuss, that is the controlled thermonuclear fusion. Controlled thermonuclear fusion. In this category, as we have studied that it is difficult to build a controlled thermonuclear fission, and the many countries of like India also, they all are trying to build such kind of the powers. So in that, the main requirement for that controlled fusion reactors are, number one, that is the very first is the high temperature. The high temperature means near about 10 raised to the power 10 Kelvin of the temperature is needed for that particle to fuse and becomes a big nucleus. At this temperature, the source of the deuterons forms the neutral plasma. What does it mean? It means it is the temperature which is required to form that bigger nucleus with the help of two small nucleus. The temperature which is required for that, it is 10 raised to the power 10 Kelvin. Number 2, that is the high number density. The high number of density of the particle is required for the high collision rate. So as much as the collision rate is high, the amount of heat is more. So ultimately the product efficiency will be more. The third one, which we can say, that the duration. It will be a long duration of such high temperature and high number of density, so that the particle may be fused together. So it will take a long time. So these are some primary requirement for the controlled thermonuclear fissions.